circular functions. Let's talk a little bit about them. So circular functions are also one of those things that people find really annoying, and fair enough, they are quite complicated, especially when you're graphing or solving for them. So when we think about circular functions, what we think about is the unit circle. So that beautiful circle which is 1, -1, 1, -1. In a unit circle, the easiest way to think about it is the y-coordinate is the sine and the x-coordinate is the cos. And then the tan is the gradient, so y over x. In methods, we just use radians for angles, okay? Like in 1, 2, you would have used degrees sometimes, but for 3, 4, generally everything is in radians. So if your calculator is still in degrees, I would recommend for you to pop it into radians, and then just be careful about whenever you see questions about angles or anything, just be careful about what they're actually asking and whether they're asking for radians or whether they're asking for degrees in the first place. So the next thing you need to know is how to remember your exact values. There's 3 different ways. This is the table way. Okay, so table way. So if we look at this is what it's going to be. So this is an angle of 0. This is going to be an angle of pi on 6. This is going to be an angle of pi on 4. It's going to be an angle of pi on 3. And this is going to be an angle of pi on 2. So just remember, those are the key angles you need to remember. There's 3 different ways. 1, the hand method. 2, table. 3, triangle. This is my preferred method because it's the least memorizey. People do use the hand method as well. Look up a video on YouTube. It's quite beautiful. You basically just like count over the fingers and then count backwards to kind of figure out what's going on. So it's also quite good, but you just need to remember the order of the angles quite specifically. Table is good, especially if you're regurgitating a lot of numbers that you need to use. But I find, so the 2 triangles that for this are the first triangle, which is the 1, 1, root 2 triangle. So that's the pi on 4 triangle. And the other triangle is the 2, 1, root 3 triangle, which is the pi on 3, and this one is pi on 6. And using the triangle, you basically use SOHCAHTOA to find out what each of them are. Cool. Alright, so solving. There is 2 kind of different ways to talk about solving. So the easiest way is to rearrange for a simple equation. So what you're going to try and do is put everything outside of your sine, cos, tan to the other side. So you're going to chuck everything onto the other side. Then what you're going to do is try and find the base angle. So what angle would correspond to the value on the other side? Now, for sine and cos, you want 2 solutions. And why you want 2 solutions is if we consider sine, right? The 2 solutions are located, they're located here and here. And for cos, it's located here and here, right? Because sine, if we think of the one, it's ASTC. So you can do cast for the ones which are positive. Alternatively, you can look at which side's positive, which side's negative, x-axis, y-axis as well. So if we consider sine is positive in those 2, cos is positive in those 2. And we can kind of see like the actual like solutions, they're not evenly spaced from each other. So that means for cos and sine, we need to find 2 solutions per cycle, versus tan, because the positive solutions are here and here. So they're evenly spaced from each other. So that means that we actually don't need to do, that's why our period for tan is only pi rather than 2 pi, because it actually is evenly spaced compared to these 2. So we need to find 2 solutions for sine and cos. Alright, so then you do a quadrant check, which quadrant it is, and you can find 2 solutions for between 0 to 2 pi, and then you just add or plus or minus 2 pi until to fill out the domain, and then you can solve for x. Alternatively, you can kind of skip this step and just solve for x first, and then what you do is you add whatever their period is. So add period. So if their period was 2 pi on 3, you add 2 pi on 3. If their period was pi on 4, you add pi on 4. If their period was 2 pi, you add 2 pi. So let's have a go at doing that. So this needs to be solved over an interval of 0 to 4 pi. Alright, so the first step, we're going to move everything around the sine to the other side. So that's going to be sine x will just equal to a half. Now a second step is to find the base angle, which means we need to refer back to what we were kind of looking at before, so the triangle. Right. And we identified that we want the 1, 2, root 3 triangle here, so 2, 1, root 3. So that's going to be up high on 3, and that's going to be up high on 6. And remember, this triangle is just derived from an equilateral triangle with 2, 2, 2 on each side. Okay, so what we can see here, that's 1 over 2, and we want sine, right? So 1 over 2 would mean it needs to be the opposite of whatever it is. So 1 over 2, that means that it needs to be pi on 6. So our base angle is pi on 6. Alright, let's do our circle next. So in terms of our unit circle, we're going to think it's here and here, right? Because we're thinking these are the areas which their y coordinate is positive, so that's where sine is positive. So the two angles we're going to be thinking of is pi on 6 and pi minus pi on 6, right? So that's x equivalent to that. And we'll have x equivalent to pi on 6 and 5 pi on 6. Okay, cool. Now we need to check for the domain. So those two solutions are in domain, happiness. So if we check minusing, that would become negative 11 on pi and negative 11 over 6 pi, and that would become negative 7 over 6 pi. So that's outside the domain, so we don't want to go backwards. Now we can check with forwards. So if we go, that's pi on 6, that's 5 pi on 6. Now if we go forwards, that's plusing 12 pi on 6. So we're going to have 13 pi on 6, and the other one is going to be 17 pi on 6. And we can check those, so that would be 24 pi on 6. And that's going to be within domain. Alright, if we tried to add 2 more pi, immediately we can tell that if we added that would be 25 pi on 6. So it's already outside domain. So these are our final solutions. Okay, so those are kind of you might get a question or two of those in exam 1 or on one of your SACs. Importantly, you also might get questions like this where you kind of have compound functions which you need to solve together. And people get really freaked out about these, and kind of fairly so. So what we want to actually do is you want to think back to your polynomial knowledge. Pretend that all of those causes are just a's and you're just factorizing as much as possible, okay? So what you want to do is group like terms, factorize as much as possible, and then treat the causes like x's, and then solve for cos afterwards. And it's going to apply the same way when you have an exponential as well. Sometimes you'll have something like either 2x plus, I don't know, 5e to the x minus 3 or something, and you'll freak out and the first time you see it, and then you won't freak out after that, because all you need to do is just sub in a equals either x, and then it just turns into a quadratic which you can solve, and then you can kind of revert backwards after. And it's the same for kind of these circular functions. So whenever you see something a bit unfamiliar and it's in exam 1 and you know, oh, I can't use my calculator for this, there's going to be some method where you kind of replace one of the factors to make it more comfortable and to make it something you know better. Cool. Yeah, and never divide out factors, just in general, not just in circular functions, just in general. You will lose solutions. You can always remove solutions after and say, oh, this is why I'm removing it, but you can't just like kick them into space, outer space, and not tell why we're kicking them out into outer space. Okay, so general solutions are a way also to represent circular functions, and there is formulas for general solutions which can be given in like your books and stuff, so you can have a look at those. I personally don't find them like they're good, right? But I didn't use them that much in VCE. I kind of just build it up a different way, and I always found that worked out better because it just made a little bit more sense to me. But you can see which one works better for you, whether you prefer the formula more or you prefer this method more. It's kind of up to you what you want to use. And because of the cyclic nature of the unit circle, we can really get infinite solutions. And that's why we go for general solutions. So if they don't give you a domain, they're asking you to find the general solution. Cool. So it's asking us to find the general solution of cos x equals to tan x. Alrighty, so 2 cos x minus tan x. And why I'm taking it to the other side first is I want to avoid any incidents of me just randomly removing solutions. that equals to 1. All right. So the first thing I'm going to do is I'm going to rewrite this tan x as sine x over cos x. Right? And that's going to equal to 1. Now, what I'm going to do after this is I'm going to change this so this is all over the same, like just basically times everything by it. So I'm going to get 2 cos squared x minus sine x equals 2 cos x. Right? Cool. Then once again, what I'm going to do is just move everything to the other side. So 2 cos squared x minus sine x minus cos x. And that now equals to 0. Cool. So then what we can do after this is we can kind of consider like what we want to in terms of the grouping and how we can group the different things together, right? Because now we have our cos x's and we have our sine x's, all of these kind of all together now. So what we can do here is we have our 2 cos x squared. So just like for this previous question here, when we had our 2 sine squared x times cos x minus our cos x, right? What we can do here is we can kind of do something similar where we're going to try and take out the components that we already have, right? And we're going to try and take out like what we can see which is common between the two. So if we kind of move back onto this page, the first thing that we can kind of take out here is going to be our cos x, right? Which is going to revert us back to here. Wait, let me just rub that out. So what we're going to try and do here is, so we need our 2 cos x equal to be equivalent to our tan x. So let me think of a good way. Oh, wait, yes. So a good way to do this is not to write 1 on the other side. Okay, oopsies, sorry guys. This should just be 0. Because I cannot minus. Apologies for that. Alright, so let me just write in a 0 here. Because when we took tan to the other side, it should equal to 0, shouldn't it? Alright, so when we put that onto the other side, now we can times everything by that. That would still equal to 0. Okay, so now what we can do is, so we've got this cos squared x now is equivalent to kind of this negative sine x, right? So if we kind of consider this as cos x minus our tan x, and we have a look at our kind of unit circle, right? Oopsie. Why won't this work? Oopsie. Okay, I'll just use it on this side. Right away, for what we can actually tell from this one, using our knowledge from talking about minimal domains and stuff like that, is that cos x will not equal to 0, right? So we know that x immediately cannot equal to pi on 2 or 3 pi on 2, or basically, if we talk about in general solutions, it can't equal to 2 pi plus 1 over 2. Yeah. So then we kind of go back to this cos squared x minus our sine squared x equaling to 0, right? And we want to change this so it's something that we can deal with now, right? Because we have this cos squared x and we have this sine squared x, and we kind of figured this out already. So what we're going to do here is we're going to just plug in 1 minus sine squared x minus sine x equaling to 0. Because remember, cos squared x plus sine squared x equals to 1. And that's our Pythag theorem, which is really helpful, right? So if we removed kind of to get cos squared x by itself, kind of change that to the other side. So now what we're going to get here is 2 minus 2 sine squared x minus sine x equaling to 0. And we can do we basically, like I talked about before, we now have this squared part, which is really hard to deal with. So we're going to just change that to a, and instead now we're going to have 2 minus 2a squared minus a, and that equals to 0. Now we can kind of just do a bit of a quadratic type of thing. And what we're going to do here is we're going to say a is now equivalent to 1 plus or minus root 4ac. So b squared minus 4ac, so that's negative 1 squared minus 4, a, which is negative 2, c, which is just 2, over 2a, which is negative 4. Right? So we get that. Alright, so then we get a equals to 1 plus or minus, and we can note that that's going to be negative 2 times 2, which is 4. 4 times, so negative 4 times 4 is going to be negative 16, right? So that's going to just be 16, negative 16. And then what we're going to get here is that it's just going to be equivalent to, so 1 plus that is going to be 1 plus or minus 17 over negative 4, right? Okay, so you can also rewrite this as a squared plus a minus 2 as well if we wanted to. Doesn't really matter either way, I guess. Alright, so then we get to this part, which makes life a little bit trickier, I think, because now we have this fraction. I definitely don't think this is something you probably can solve by hand. So then we can go to our trusty calculators to try and find what it's equivalent to. Algebra solve. And I know it kind of can seem a bit silly to revert to our calculators now, but sometimes we do need to get it into a specific form. And I think that this form was just not something that we could unfortunately do by hand. So let's plug this into our calculators. Just make sure it's on radians. Hopefully my calculator doesn't do the wheel of death, but it did give me a very approximate answer, which is definitely not a good sign. So it gave me that, let's try and just solve this so we can actually find what our thing is first. 2a squared plus a minus 2 equals to 0 for a. So yeah, so essentially it's giving us numbers which are like x equivalent to 0.895 ... and that's in radians, by the way, so however many of that, and then x equals to 2.24 ... So essentially after this step, if this equaled to like a half or something that was easy to do, you would just make it equivalent to sine x, and then you can solve from there. But unfortunately, because it is equivalent, so those are our two base angles, we can convert these to degrees, because it might be easier to work with. Well, it doesn't really matter either way. So the main thing is that we can see here that the period of this is just going to be 2 pi over 1. So it's just going to be 2 pi. So it's going to be whatever this is, plus 2 pi n, plus 2 pi n, because we're just adding the period, so it should be the same. Then we're going to say where n belongs to z. Cool. Awesome. So yeah, that's kind of how it works. If this was a nicer number, we probably could do it fully by hand, but because it was a bit of a gross number, we couldn't really do it by hand for the full process. But once you get to this step, if this, in a question which you can do by hand, you should get a half or something, or like a half, root 3 on 2, 1, root 2 on 2. That's really the only things you can really get. Cool. Alright, so in terms of graphing, the easiest thing, let's just talk through the graphing, kind of the steps. So the steps I like to talk about is do period amplitude, do a dotted line at the mean line, talk about where the mean and the max are. Then you determine the quarter or the step size, and you divide the period by 4. And what you do is you kind of dot those periods along. And then what you can do after that is find out where it starts. So when it is at its max or when it's at its min, and then just kind of dot those along from there, and then you just mark the important points from there, and then you just repeat until you get more periods. Cool. So let's put this into practice a little bit. So I'm going to start off with my amplitude, and my amplitude is 2 here. My period is 2 pi over 1, so that's just 2 pi. My max is going to be 2. My min is going to be -2. And my mean is just going to be 0. So that means that I don't need to find x-intercepts for that one. Hurrah. Okay. So then after this, I find what my step size is. And my step size is going to help me determine how often I move from my max, my mean, to my min. Okay. And that's how often I'll move. And that's going to be 2 pi over 4, or otherwise known as pi on 2. Then I'm going to choose where it starts. So x minus pi on 2, if we consider like the kind of just the normal graph of what a cos graph really looks like, a cos graph kind of looks something like this, where it kind of goes like weep, weep, and kind of goes like that, right? So this will be at pi, and this will be at 0, and this is kind of at pi on 2. Now we have this minus pi on 2, which means that it's actually shifted right pi on 2. So what's going to happen is now my top point is going to be here, and now my bottom point is going to be here, and this is going to be here, right? So now my maximum is going to be at pi on 2 instead. So what my starting point is going to be pi on 2, and I can see that's pi on 2, 2, right? So starting point. Right. And then you're basically ready to do. You could also find x-intercepts, but for this one's not strictly necessary. So let's make sure we label our axis appropriately. And if you're able to kind of label it appropriately, I really recommend you kind of choose your own spacing, because it does make your life a lot easier. 3 pi on 2, pi on 2. Cool. And I'm going to say 2, -2. Okay, so I know I'm going to start here. And then what I'm going to do is move my step size, so that's pi on 2. And when I do that, I'm going to move to the mean line, either side. Right? Okay, so I've hit the edges of my domain on the 0, so I don't need to go back further. Now I just need to go forward. So I've hit pi, right? Now I'm going to move forward another pi on 2, and now I'm going to go from my mean to my min. Okay, cool. Now what I'm going to do is now move another pi on 2, and now I'm going to go back again to my mean. Alright, now then we just join the dots. And we are done. So that's pi on 2, 2. And 3 pi on 2, -2. Then we have 0, 0, pi 0, 2 pi 0. Okay, so generally in a circular function graph, what you have to label are the min, the max points, and the x-intercepts. If your mean points don't hit the x-intercept line, I'll just not label it, because you already label so much stuff, it just makes everything a bit messy. So I would just not label those. But for this one, because it hit the x-intercepts, we have to label them.